Let's check out my new animation of IMAN. Well, there you go. That's the logo. It's the logo of your school animated. Let's see that again. There you go. Alright, let's start the topic. The topic is going to be current in circuits. Well, what is this all about? I'm going to need to get the current that is going to be coming out of the battery when it's connected to this big circuit with resistors that are in series, and some of them are in parallel, so it's a combination of the two. So the new thing is going to be finding the current that is going to be coming out of this battery and going inside this circuit. So what do we do? What do we have to do, guys? Well, I have to identify what is in series. So for example, you could say, oh teacher, this 10 and this 10 are in series. But it's not, because as I have told you before, there's something here in between. This thing won't let it be in series. There's something here that's a problem, but between this guy and this other guy, they have just one connection. There's only one path for the electrons to flow in. That makes it a series connection. So I gotta put these guys together. I'm gonna add them. 10 plus 10, boom, it's 20. You got your new resistor. It's in series. All you have to do is just add them. It's gonna be 20. And we're getting closer to get the current. Again, this is the whole point of this problem, to get the current of this circuit. But before I can get the current, I gotta simplify the whole circuit into one resistor. So I got this 20 ohms, and I got this 10 ohms, and you see this resistor and this resistor, they are sharing one terminal, and it's sharing another terminal. Alrighty, sharing these two terminals. That makes it, you guessed it, parallel. These guys are in parallel, so what you have to do is do 20. Okay, no, it's going to be 1 over 20 plus 1 over 10, and then you got to do 1 over this, 1 over all of this, and it's going to give us the result. Or you can also do this trick. You can do this: 20 times 10 divided by 20 plus 10. Okay? And that will give us the result. Alright, how much is that going to be? It's going to be 6.66. Now, what's going to be next? We got these two resistors. Well, they are, as you can see here, they just have one connection. That's called series. So we got a series connection right there. We got to put these two resistors together. What do we get? 6.66 plus 10. You got it. 16.66. That is going to be the equivalent resistance of the big circuit that we had before. So the other big circuit for the battery, it just looks like one resistor of 16.66. And for the battery, relative to the battery, we can apply the law of Ohm's law. Remember Ohm's law? It's voltage equals intensity times resistance. That is Ohm's law, and we can apply it to that big circuit, but only when we have it simplified, which is what we have done just right now. We got that resistance because before we had like 6 resistances. Where do I apply it? Where do I apply my 5 volts? what do? We can't just apply it directly. We had to simplify it first. So we simplified that big network of resistors and we changed it into just one equivalent resistance, which is that one. Now with this information, now I can get the current flowing from here to here. That current, how much amps, how many amperes, how much current is flowing in this circuit. That's what we will get. And I'm going to be using the formula for Ohm's law. But I got to clear it for intensity. So intensity is going to be, well, you see the resistance is multiplying. I got to pass that to the other side, which is the same as doing division on both sides with the resistance. That'll be voltage divided by resistance. So now all I have to do is just divide the voltage by this resistance, and that's it. That's the current. That's how much current will be coming out from this battery when you connect it into this big circuit. So the current, it's not going to be just, oh, I'm going to divide the 5 with this 10. That's going to be the current. Nope, 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 because that current is going to be supplying not just this resistor, but also these other resistors. And to know how much current there's going to be, well, we got to simplify this whole network, this circuit. Alrighty guys, well that's pretty much it for intensity. But I got another topic for you, so this is a 2-for-1. I got also power. I'm going to give you this other topic of power. Power, as you remember from physics part 1, season 1 of physics, power was the work over the time. That was power. And the work was measured in joules, and the time was measured in seconds. And remember how much power was? What was the unit for power? It was the watt. Okay, so this is watts and this is work. Let's not confuse them. Okay, so we got power in watts. Now remember that we have some work here, and remember the definition for voltage. Voltage is work over charge, and current is charge over time. So do you see a relationship between the work and the time? Well, it's right there, guys. It's all there. What if I combine the work into this equation? I say, oh yeah, work, that's going to be just voltage times charge. I'm going to clear for work. Now I'm going to do the following. I'm going to place this thing into this formula, and let's see what we got from that combination. Let's see, power equals, instead of the work, I'm going to write voltage times charge over the time. Whoa, what's going on here? Wait a minute. Wait a minute. This is charge over time. Charge over time. That reminds me of something. Right here. It's the current. So that means that the power is going to be voltage times the current. That's going to be the power formula for when you have circuits or electricity. This one is going to be the general case for when you're walking around and you using your work, how much work you do, your workout. But when we're talking about circuits, this is it. This is it. That's the one we'll be using. Alrighty then, let's continue. We got power equals voltage times current. And just the same as before, in season 1 of physics, back then, we measured power in watts. So I'm going to give you an example that you guys are very familiar with. I'm going to take a light bulb from your house, and that light bulb is going to have 100 watts. Let's imagine that it's one of those classic old light bulbs that you've seen around. Well, today we got different light bulbs. For example, this one. This is a halogen light bulb, and it uses less energy than those classic bulbs that we used to have. As you can see, this one uses a power of 100 watts, and this one uses 23 watts. It's more eco-friendly. Eco-friendly, guys. It's not just eco-friendly, it's also friendly on your wallet, because it's going to be using less energy. Okay, so let's get the current for this light bulb. The intensity, as you remember, oh no, we don't remember. I gotta clear this formula. I got power equals voltage times current. So what I'm gonna do is, I know the power that this thing has. It has 100 watts. So the power rating on a device, for example, your refrigerator, your microwave oven, your, I don't know, like anything that you have around you, your power, your computer has also a power rating. If you look closely, or also your charger, look close enough, and you're gonna find a label that says the wattage, the power, and it's gonna be telling you how much energy it consumes. So this light bulb consumes 100 watts. So remember what watt means. Let's go back to this definition that we used to have. It was joules per seconds. It's watts, work per time. So it's going to be how much energy it's going to be consuming every second. How many joules are going to be used up in a second. And that is going to be what they will be using to charge the electricity when you get the bill. They use wattage, how much energy has been consumed. They don't measure the voltage or the current, they measure it in watts. And also, the light bulbs, how much energy it consumes, they tell you, okay, this light bulb is going to use up 100 watts. And that means that it's going to depend on how many voltages, how many volts you're going to use. And it doesn't matter how many volts you use, it's always going to have this power, because that's how it's designed. Alrighty guys, what are we going to talk about? What's going to be the problem that I'm going to be solving here? It's going to be, okay, we know the light bulb, it's 100 watts. And we know that when you connect it into your house, you get 120 volts. How much current is going to be flowing through this light bulb? That's going to be the question. So we got power. Power is 100 watts. And the voltage is 120 volts. So I'm going to take this equation, and I know that this thing is multiplying. The voltage multiplies the current. I want to have current by itself forever alone. I want to have it by itself. I'm going to clear for the current. That voltage is multiplying. I'm going to pass it as a division. So it's power over voltage. Power over voltage. 100 watts over the 120 volts. That's going to be 0.83 amperes. So that classic light bulb of 100 watts, when you connect it to your plug in your house, it's going to be using up 0.83 amperes. 0.83 amperes. But if you use another eco-friendly light bulb such as this one, which uses 23 watts, it's going to be telling you how much it's going to be telling you how much energy is going to be used up every second. So every second that passes, 23 joules are going to be absorbed by this light bulb. 23 joules, guys, every second, because that's what power means. It's the energy over that time. It's joules over seconds. Alrighty, guys, so this one uses up more energy than this one, even though it gives you the same amount of light. So because we got different technologies. This one uses an older technology, but this one uses some other form, which I'm not going to touch, which I'm not going to be going into it, but I'm just telling you it's different. But we are going to see the current that is going to be absorbed by this light bulb. And I'm going to use the same formula as in the previous case. I'm going to do power over voltage. I know that this one, eco-friendly, uses 23 watts, and I'm going to divide that by the voltage, which is 120. Make this division, get 0.19 amperes, which means that this one uses less current than this one. And as you remember from the previous discussion a while ago when we were talking about current in your house, it has a limit. And if you're consuming too much current, that's going to be a problem. It's a hazard, uses too much energy, which changes into heat. It's going to be a big problem. So it's better if you use less current. So get these light bulbs, guys, these eco-friendly light bulbs. But you know what? I'm curious, guys. I'm a little curious right now, and I want to know what's going to be the resistance for this light bulb. Now that I have the power, I know I got current, got voltage. How about we get the resistance for this light bulb? What are we going to do? Well, that's what I'm going to show you right now. But also, I want to tell you that the resistance, any device has a resistance. A light bulb is a resistance. And this resistance, when you get electricity flowing through this wire, it heats up and emits photons. You know what photons are? Those are the particles that make light. Alright, anyways, let's continue over here. I'm going to give you another formula for the power. But to get it, I'm going to use the definition for the law of Ohm, which is this one. And now I'm going to combine this formula with this other formula and this formula with the power formula in a very interesting way to get new formulas for power. And I'm going to show you when it's going to be appropriate to use that other equation. Okay, so I'm going to take this equation of power, and I see that I got a voltage right here, and I know that voltage is the same as current times resistance. So that means that I'm going to be taking the voltage here. There you go. That voltage right there. I'm going to be substituting it for what I know voltage is. And I know that voltage is current times resistance. So instead of the voltage, I'm going to replace it with intensity times resistance, the current times resistance. And that's what I have right there. Now I'm going to be rearranging my terms here, my factors. This I is multiplying everything else. Well, I'm just going to move it a little bit over here just to make it clear that I want to multiply the I with the I, which give us intensity to the power of 2. Well, we have our new formula. Now, what do you see that you don't have over here? This formula only has current and resistance. So this is going to be very good for one example. You know the intensity and you know the resistance, but you don't know the voltage. Maybe it's not on the legend of your power source. You only know the current that it absorbs, and you know the resistance, but you don't know the voltage for some device or something. In that case, you got to use this formula. But if you know the voltage and the current, you can use this formula. But if you don't know either one of them, but you do know the current and the resistance, you can use this formula instead of this one. Now I'm going to use again the law of Ohm, and I'm going to clear for current, and it's going to be like this. I see that this voltage is multiplying the I. I'm going to pass it to the other side, and it's going to be it's over here. Where is it? Oh, no. Okay, sorry. You know what? This thing is going to stay the same. What I'm going to change is actually this formula. I'm going to change this formula. This I is multiplying the R, so I'm going to clear for the I. That R is multiplying, so I'm going to pass it as a division, which is what I got over here. Now I'm going to get a new equation for power, and it's going to be based on this idea that I'm going to show you right now. Okay, so current equals voltage over resistance. We saw that a few classes ago. And now I'm going to substitute this amount into the power formula. So instead of the current here, I'm going to place voltage over resistance. It's right there. Voltage over resistance right there. And I got the voltage here. So I'm going to multiply voltage with this voltage. How much is that going to be? Voltage to the power of 2. Then that's going to be dividing the R. There you go. So I got my second formula with the Ohm's law. I combined the Ohm's law with my power formula, and I got these two new formulas. So I got one formula for power, two formulas, three formulas. I have three formulas for power. Okay, guys, but you got to use this one, for example, when you don't know the intensity. You only know the resistance and the voltage to know the power for that case. And this one you're going to use it when you know the resistance and the current but not the voltage. And this one you're going to use when you only know the voltage and the current. So those would be the appropriate cases to use them. Now, what if I want to know the resistance that I was telling you about a while ago of this light bulb? How can we get the resistance? Well, now we have the formula that combines power and voltage with the resistance. I know that power is voltage to the power of 2. Power is voltage to the power of 2 divided by resistance. So then I'm going to use this formula in order to get the resistance of this light bulb. This resistance is dividing. I don't want it there because I want to have it by itself. So I got to pass it over here. I got to multiply everything by R, and the R is going to now multiply the P. R times P equals B squared. That's going to be my next step that I did for my algebra. And now I want to have the R by itself, so this P is multiplying. I do not want it there. That P is going to be dividing. It's going to go over here. There you go. It's going to be B to the power of 2 divided by P. B squared voltage is going to be 120 volts to the power of 2 divided by the power that I know, that this light bulb will be absorbing 100 watts. So you got to do 120 to the power of 2 and then divide by this. That will be 144 ohms. So that's going to be the resistance of a light bulb. It has a resistance, guys. All the devices that you use have resistance. And you can calculate it if you know the voltage that it consumes and the power that it consumes. For example, if you check your power source from your cell phone, it's going to give you your power source. What do I mean by that? I mean your charger, your phone charger or whatever. It's going to give you an amount of voltage. It's going to give you an amount of, the watts, and it's not going to give you the resistance, but with this formula you can know the resistance of your device. Alrighty guys, anyways, well, that's pretty much it. If you have any more doubts, questions about the problems, you know where to find me. You guys have a great day. I will see you later.